Hello, I'm Kashish Raveri from IPM05 batch. I'm going to be explaining about queues. A queue is a useful data structure in programming. It is similar to the ticket queue outside a cinema hall, where the first person entering the queue is the first person who gets the ticket. Queue follows the first in first out FIFO rule. The item that goes in first is the item that comes out first. As we can see in the picture, since 1 was kept in the queue before 2, it is the first to be removed from the queue as well. It follows the FIFO rule. In programming terms, putting items in the queue is called enqueue and removing items from the queue is called dequeue. Now let's discuss the four main types of queues, which are simple queue, circular queue, priority queue, and double-ended queue. First is the simple queue. In a simple queue, insertion takes place at the rear and removal occurs at the front. It strictly follows the FIFO rule, as seen in the picture. Next is the circular queue. In a circular queue, the last element points to the first element, making a circular link, as we can see in the picture here. The main advantage of a circular queue over a simple queue is better memory utilization. If the last position is full and the first position is empty, we can insert an element in the first position. This action is not possible in a simple queue. Now let's look at the priority queue. A priority queue is a special type of queue in which each element is associated with a priority and is served according to its priority. If elements with the same priority occur, they are served according to their order in the queue, as shown in the picture. Insertion occurs based on the arrival of the values and removal occurs based on priority. The last type is dequeue, also known as double-ended queue. In a double-ended queue, insertion and removal of elements can be performed from either the rear or the front. Thus, it does not follow the FIFO first in first out rule. Here is a representation of this type. Next, we'll be discussing the queue operations, which would be followed by my team.
Hello, I'm Joshil Jain from IPM05 and today I'm going to present about operations on queues. So let's first see the first operation, the enqueue operation, which adds an element to the rear of the queue. The queue grows as we add more elements and this happens in a constant time period, which is also O1. This is because we're only placing the new element at the end of the queue and we don't need to shift any other element. So here's a video animation that shows how the enqueue function works. Let's see it. We now move to the next operation, which is dequeue. The dequeue operation removes the element from the front of the queue. Like enqueue, dequeue also operates in O1 time because we're just removing the first element without needing to shift others. Here's an animation that shows how the dequeue function works. Now let's look at the code snippets or pseudocodes that show how enqueue works, enqueue on the left and dequeue on the right. Now let's see the next operation, which is peek, or which is also called front. The peek or front operation simply allows us to see the front element without removing it. This is very useful when we need to check what's next in line but don't want to disturb the queue. Like the other operations, peek also operates in O1 time since it just returns the value at the front. Also, here's a pseudocode that shows how the peek command, peek function is working. We can now see the next function, which is isEmpty. The isEmpty operation checks if the queue is empty. This is a quick check and also runs in O1 time. It is crucial to prevent errors like trying to dequeue from an empty queue. Also, here's an animation that shows how exactly does the isEmpty function works. Moving on to the next operation, isFull. In the case of fixed size queues, we have an operation called which is isFull. It checks whether the queue has reached its maximum capacity. This is important in systems where memory or space is limited. Again, we have a video which shows how isFull works. To conclude, to sum up, queues are crucial in many real-world scenarios where order and efficiency matters. The main operations enqueue, dequeue, peek, isEmpty, isFull, all of the operations that we saw throughout this section, all operate in constant time, making queues a highly efficient data structure. They are widely being used in systems in task management, process scheduling, and buffering. In the next session, we are going to see how this is exactly implemented.
Hello, I'm Angel Sidhu from the IPM05 batch. Today, I'm going to discuss the simplest implementation method of a queue, that is the array implementation of a queue. So what is array implementation? Under this method, the queue is implemented with the help of an array of fixed size n. The queue, which is a linear data structure, follows the FIFO, that is the first in, first out principle. This means that the first element that is added to the queue will be the first one to be removed from the queue as well. In this array-based implementation, we maintain two pointers, the front pointer and the rear pointer. The front pointer indicates the position of the first element in the queue and it is initialized at 0, whereas the rear pointer indicates the position of the last element and is initialized at -1, as there are no elements in the queue initially. We can see in the example given below that the front pointer is at index 0, whereas the rear pointer is at index 4. However, if the last element wasn't there, then the rear pointer would be at index 3. When we add an element to the queue, this operation is called enqueue that we're now going to discuss. Before adding an element, we must check if the queue is full. This is done by verifying if the rear pointer has reached the maximum capacity of the array. If this condition is true, we encounter an overflow condition, and the enqueue operation cannot proceed. If the queue is not full, we increment the rear pointer by 1 and insert the new element at that position, as can be seen by the animation. We can see that with every enqueue operation, we incremented the rear pointer by 1. Now coming on to the dequeue operation. The operation for removing an element from the queue is called dequeue. Dequeue can only be performed if there is at least one element in the queue. If the rear pointer is at -1, it indicates that the queue is empty and we have encountered the underflow condition. When dequeuing, we remove the element at the front of the array. So, as can be seen by the animation, to dequeue, we simply increment the front pointer of the array. Now, when all the elements have been dequeued and the rear pointer is at the last index, if we attempt to perform an enqueue operation, an overflow condition will be exhibited. Though there is freed up space in the front of the array, which we can use, we really can't use it in this method. So this is one of the major limitations of the array implementation method of a queue. However, this can be solved. To address this issue, we can implement a circular array. A circular queue is an extended version of a normal queue. The last element of this queue is connected to the first element of the queue, thereby forming a circle. In a circular queue, when the rear pointer reaches the end of the array, it wraps around and starts storing elements at the beginning of the array, provided that there is available space at the beginning of the array. This makes efficient use of the array and eliminates any need to shift the elements after every dequeue operation is performed.
Hello everyone. Today I Gaurav Shekhawat will be talking about the linked list based implementation of a queue, which is a dynamic and efficient way to handle data in first in and first out order. In computer science, a linked list is a linear data structure where each element is a node containing two parts: data, the value stored in the node, and the pointer, a reference to the next node in the sequence. Now, when implementing a queue using a linked list, we use this dynamic structure to store our queue elements instead of using a fixed size array. Now, let's compare various scenarios where using a linked list is better than using array implementation. Unlike arrays, linked lists grow and shrink in size dynamically, making them ideal for situations where we don't know the size of the queue in advance. Adding or removing element is efficient because no shifting of element is required, as it would be in an array. We just adjust the pointers in the linked list, because of which the time complexity of the enqueue and dequeue operation in linked list is also reduced to O of 1. Linked lists use memory more efficiently because they allocate memory only when needed for each element. Unlike arrays, on the other hand, can waste memory if their allocated size is larger than the number of elements being used, which results in unused space. Linked lists do not require contiguous memory allocation, since each node points to the next node. With a linked list based queue, we maintain two pointers. The front pointer, this points to the first element of the queue, which will be removed first during a dequeue operation. Rear, this points to the last element where new data is added when we perform an enqueue operation. Now let us look at a code where we use linked list based implementation. In this code, we implement a queue using a singly linked list, which dynamically manages the elements. First, we have a node class that represents each individual element in the linked list. Each node stores two things: the data and a pointer. Next, that link that links it to the next node in the queue. Then we have the queue class, which maintains two pointers, front and rear, to track the beginning and the end of the queue. There are various operations in this code. Now let's look at them. First, the enqueue function. A new node is added to the rear of the queue and the rear pointer is updated to the point to this new node. The dequeue function, where we remove the node at the front and adjust the front pointer to the next node. If the queue becomes empty, after this operation, both front and rear are set to none. There are also other methods like other functions like isEmpty, which checks if the queue is empty, and getFront and getRear, which retrieve the data from the front and rear elements respectively. This linked list approach ensures that the queue can dynamically grow and shrink without wasting memory or requiring a fixed size. Now you can look at the solution of this code when we execute it. It gives us the queue front, queue rear, queue front, and queue rear after the various enqueue and dequeue operations. Thank you.
Hello, I'm Kashish Javeri from IPM05. Now let's look at the applications of queues in real life. First, customer service systems. In call centers or customer support, queues manage incoming calls or requests, ensuring that customers are attended to in the order they arrive. That is, first come, first served. Second, order processing. E commerce platforms use queues to manage incoming orders, ensuring that they are processed in the order they were received, which helps maintain fairness and efficiency. Third, print spooling. In printing services, print jobs are placed in a queue to be processed one at a time, preventing conflicts and ensuring orderly execution. Fourth, banking systems. Queues are employed in banks to manage customer transactions, ensuring that customers are served in the order they arrive at the counter. Fifth, appointment scheduling. Healthcare systems use queues to manage patient appointments, ensuring that patients are seen in the order they booked their appointments. Thank you.
My name is Chandrasekhar from IPM05. I am explaining three major applications of queues in our day-to-day life. The first application is round-robin scheduling in operating systems. It is a common method used in operating systems. In multitasking environments, several processes need to share the CPU. The queue process here is critical. Each process is placed in a queue and the CPU allocates a fixed time slice to each one in turn. This ensures that every process gets a chance to run and no single task dominates. The round robin is particularly important in real time systems where timely task execution is essential, like web servers. And the second application is call centers queues. I'm sure we all have a experience of waiting on the phone for customer service. When a customer calls, they're placed in a queue until agent becomes available. This queue operates first in first out manner, meaning the first customer who called to the server, he ensures the first to be talked. This ensures fairness and efficient management of incoming calls, preventing inefficiency during peak hours. This system helps business to maintain a good customer service and reduce wait times. And the third application is packet scheduling in networking. When you send data over the internet, the data is broken into smaller units called packets. Routers use queues process to manage these packets before forwarding them to the next node in the network. This ensures that packets are delivered in the right order and network congestion is avoided. Without packet queuing, data loss would be a common and communication delay would increase significantly, affecting things like video streaming and online gaming. Thank you.
Hi, I'm Yashar Marjwal from IPM05, and now I'll explain time and space complexity of queries. Now, it can be implemented in two ways, one using array-based queue, and second using linked list-based queue. Now, even though both methods are a bit different, they have same time complexity for the basic operations. Now, these are the main operations of the queue, which is enqueue, dequeue, peak, and lastly, is empty or is full. Now, let's see time complexity of each one by one. So, starting with enqueue operations, which means adding an item to the back of the queue. If we use an array for the queue, we add an item at the rear index. If the queue is circular, which means the end of the array wraps around to the beginning, we have to make sure the rear end pointers wrap around too. Since this operation does not involve shifting elements or traversing the queue, it takes a constant O1 time complexity. Now, in linked list queue, we don't worry about wrapping around. Instead, we create a new node and link it to the end of the queue. Here, the time complexity is also O1, which is constant. Now, let's talk about dequeue operation, which involves removing an item from the front of the queue. In an array-based queue, we remove the item from the front index and move the front pointer to the next spot. If it's a circular array, we make sure the front pointers wrap around when it reaches the end. In a linked list queue, we just move the front pointer to the next node. In both cases, since we are just moving a pointer, the operation takes O1 time complexity. Now let's look at the peak operation, which just checks what's at the front of the queue without removing it. In an array-based queue, we directly look at the front index. In a linked list queue, we look at the node that the front pointer is pointing to. Both take the same time, O1, since it's just about checking one spot. Lastly, is empty or is full, which tells us whether the queue is empty or full. In an array queue, we compare the front and rear pointers to see if the queue is empty or full. In a linked list queue, we just check if the front pointer is null, meaning the queue is empty. Linked list doesn't need to worry about being full because they grow as they need it. Now both checks are quick and take from constant time, which is O1. Since we talked about time complexity, let's talk about space complexity of queue. Now this tells us how much memory each implementation uses as the queue size grows. First, array-based queue. In an array-based queue, the space complexity is O(n). This means the queue takes up space based on the size of array, which is n. the capacity of the queue. Even if the queue has fewer elements, the array still occupies the full space because the size is fixed. The good thing is that array don't need extra memory for pointers, just the array itself and the front and rear indexes. On the other hand, a linked list based queue also has own space complexity because it works differently. Instead of using fixed size array, the memory grows as we add elements, and each element gets its own node, and each node has extra memory for pointers to the next node in the list. So while the space used by a linked list can adjust as needed, it also takes up extra memory for the pointers. Now this is all about time and space complexity of the queue.
Okay, to conclude, queues are an essential data structure that ensures orderly data processing through first in, first out principle. They are highly efficient in managing tasks and resources where maintaining order is critical, such as task scheduling, customer service system, and network data handling. Their simplicity in operations like enqueue, dequeue, and peak makes them versatile and easy to implement across both synchronous and asynchronous systems. Queues also serve as the foundation for more advanced structures like priority queue and circular queue, making them a vital component in software development. Overall, queues play a crucial role in maintaining efficiency and order in modern computing and real world applications. Thank you.